Hello, everyone, and welcome. My name is Liz Pimper, and I'll be your moderator for today's WJE webinar, Mass Concrete, Does My Project Need a Thermal Control Plan? During the next hour, WJE engineers Jacob Borgerson and Elizabeth Wagner will discuss factors that contribute to heat generation and concerns associated with mass concrete, such as thermal cracking and delayed ettringite formation. This presentation is copyrighted by Wisjani Elsner Associates. And now I will turn it over to Jacob to get us started. Jacob?
Thank you, Liz. Today we are going to be talking about mass concrete. So these are the learning objectives for today's webinar. And what I hope you guys get in addition to these learning objectives is perspective. Oftentimes in construction, we do the same things over and over and over again. And our hope is after this webinar, you'll have some different things to think about and maybe some different ways of approaching mass concrete on your specific projects. So here's an overview of the four main topics that we plan on tackling today. We want to understand how to identify mass concrete, how to specify mass concrete, what are the critical components for developing a thermal control plan, and ultimately how to execute and implement it in the field. So let's talk about mass concrete. How do we know it's mass concrete? And so as we dig into this topic, folks should understand that there are ACI references, specifically 301 and ACI 207, which is mass concrete, that can help with understanding mass concrete. And so ACI actually has a definition of mass concrete. So if you look at the ACI terminology document, they provide this wonderful definition for mass concrete. And if you read this definition, what you'll notice is the definition of mass concrete is kind of mass concrete. It doesn't specifically identify the size or the dimensions of a mass element. So what is mass concrete? Well, how is this any different than maybe a concrete slab on ground that's 6 inches in thickness? And so what we need to remember is concrete is chemical. And so I don't necessarily want you folks to understand this chemical equation that's on the slide. But what I want you to understand is that the hydration of cement is an exothermic chemical reaction. If you take a little bit of water and a little bit of cement and put your hand over it after it's been mixed, you can actually feel the heat that's being generated. If you take a lot of cement and a lot of water, you can end up with a lot of heat. And that's what we're concerned about, is the amount of heat that's being generated. And so for some mass elements, that exothermic chemical reaction can generate temperatures up to 160, 170, and in some cases, if precautions aren't taken, up to 200 degrees Fahrenheit, which is a significant amount of heat when you compare that to boiling water, for example. And so what's the problem? The big issue is cracking. And so the two things that we want to think about is thermal cracking and a phenomenon called delayed ettringite formation, which can occur later, that can also cause cracking. So let's talk about thermal cracking. How does that occur? And so here's a column, 8 foot in diameter, that had thermal cracks shortly after it was placed. And the temperature difference between the cooler surface of the concrete can contract relative to the warmer inner core of the concrete. And as a result, you end up with tensile stresses along the surface. And when those tensile stresses on the surface exceed the in-place tensile strength, you can get cracking. And so here's a schematic diagram showing the initial heat development of a mass element that's placed on a mud slab, for example, and formed up on the sides. And as that heat continues to generate on the inner core, what you'll see is the surface then cools And as those tensile stresses are introduced, you'll end up with cracking at various points along that element. One of the other things that we're concerned about is this phenomena called delayed ettringite formation. And DEF, or delayed ettringite formation, is the formation of ettringite after the concrete has already hardened, which can later cause the expansion and cracking of the concrete. And so under certain circumstances, primarily exposure to elevated temperatures during curing, the ettringite is suppressed and then may form after the concrete is hardened. And so that volume of the ettringite compound is larger than the volume of the original component materials, which can lead to the internal expansion and subsequent cracking of the hardened concrete. So Elizabeth is now going to talk about specifying mass concrete.
Thanks, Jacob. So let's go back to that ACI concrete terminology definition of mass concrete for just a minute. ACI's definition essentially says that a combination of dimensions, boundary conditions, the concrete mixture, and ambient conditions are going to lead to thermal stresses, cracking, deleterious chemical reactions like DEF, or potential reductions in long-term strength gain, all due to the elevated heat of hydration of the cementitious materials. And that's really what makes mass concrete. Now, in practice, this definition is a little bit difficult to implement into an actual specification. So a lot of specifications focus just on this first part, the dimensions. So here's an example of a mass concrete specification. This was a particular DOT specification, but you've probably or may have encountered something similar. And we'll focus just on the first sentence of this specification where it defines mass concrete placements. And this specification says that mass concrete placements are defined as placements with a least dimension greater than or equal to 5 feet or as designated on the plans. So for example, the least dimension might be the width of a column, the thickness of a foundation element, and so on. It's the smallest of the dimensions of a particular placement. And it's very common to see mass concrete definitions that are based on whatever this minimum number is. 5 feet is a number we've seen a lot. Some specifications have specified as low as 3 feet, some as high as 8 feet. And so because there's a little bit of a inconsistency, I would say, in how these are specified, there's better practices available. So let's go back to that ACI definition again. It's not just the dimensions, but really the combination of the dimensions, boundary conditions, concrete mixture proportions, and ambient conditions that make something possibly mass concrete. And so newer specifications, like I'm about to show, actually take all of these factors into account. And so here's another specification that we've dealt with. This particular specification, just like the last one, requires all elements with a section thickness greater than 3 feet or more to be considered mass concrete. But it also includes a portion that says that it's any system that approaches a maximum temperature of 158 degrees Fahrenheit within the first 72 hours. And that way, it can also include elements that are thinner than 3 feet that may have other reasons for that heat gain, whether that's related to the environmental conditions, the concrete mixture proportions, or the boundary conditions, or any combination thereof. So really, what is mass concrete? An engineer's favorite answer is it depends. And as it depends on a lot of things, ACI has recently published some revised guidance on how to define mass concrete. Specifically, ACI 207.1, which is the Guide to Mass Concrete, now talks about two categories of what they're calling mass and thermally controlled concrete. The first category is traditional mass concrete. So these are large placements that many of you probably think of when you think of mass concrete. Things like dams, abutments, foundations, slabs, very large elements where the thickness is going to govern the temperatures that are generated. But there's also this newer category that they've talked about called thermally controlled concrete. And these are typically smaller placements. And in these cases, the temperatures are more governed by the specific concrete mixtures, which have a high potential for temperature rise. And this may be because they contain a lot of cement or cementitious material, or it may be because they're designed to achieve very rapid early strength gains. The more rapid your strength gain, the higher potential you have for early age temperature rise in your mass concrete. So here's an example of how the dimensions of an element might increase concrete placement temperature. So for example, the mass concrete here is shown for an element that is increasing from 4 feet, which is the green curve, to 5 feet, blue curve, to 6 feet, which is the red curve. This is a single concrete mixture. And you can see that as the dimension increases, the maximum temperature of the concrete is also increasing. You'll also notice, and this will become important later on, that the thicker the element, it stays a higher temperature for a longer period of time. It takes a lot more time for the concrete to cool. And so that can be important when it comes to the timing and scheduling of thermal controls for a mass concrete placement. The cementitious materials similarly have an effect. And so now this graph is showing the impact of increasing the total amount of cementitious material, or the cement plus SCMs in the mix. And I'm showing here, for example, an increase from a 5-sack mix, which has 470 pounds of cementitious material, all the way to a 7-sack mix, which would have 658 pounds of cementitious material per cubic yard. And what you can see is, just like with increasing the dimension, as you increase the total amount of cementitious material in the mix, there's also an increased potential for temperature rise. Combining these two ideas, ACI 207.1 has also published this new table, which is pretty nifty. And it shows how increasing the dimension and increasing the total amount of cementitious materials interact with one another. So the dimension is increasing going from left to right, and the amount of cementitious materials in the concrete is increasing going from top to bottom. Any square that's shown in green is not going to necessarily require a thermal control plan, while anything shown in red will likely require thermal analysis or a thermal control plan. And then yellow is an in-between case. What you can see is that you can have an element that's, say, 6 feet thick, but only has 300 pounds of equivalent cement content, and that might not require a thermal control plan even though it's 6 feet thick. However, you can also have an element that's 2 feet thick that has 1,000 pounds of cementitious material. And even though that's only 2 feet thick, that's considered mass concrete because it's this class of thermally controlled concrete. And we've actually encountered situations where we've had 2-foot thick elements that we've had to write thermal control plans for because the concrete had so much cement in it. Now, once you've defined the mass concrete elements, there's another component of the specification that we'll visit. So this is actually the same DOT specification language I showed earlier, but now I'm focusing on the second half of the definition. And what it shows is that once you've defined the mass concrete placements, the next step is to develop and obtain approval for a plan or a thermal control plan that ensures that the temperature differentials do not exceed 35 degrees, and that the temperature of the central core, or the interior of the placement, does not exceed 160 degrees. Now, these limits can change from specification to specification, but the basic concept is the same, that a thermal control plan is developed to control the temperature differentials and the central core temperature of a concrete placement. So let's talk a little bit more about these thermal control plans. So like I said, thermal control plan is a document, and it will describe the specific measures that are used to control these temperatures, both the maximum temperature and the maximum temperature differences. And it also includes specific methods that are going to be used to demonstrate that these limits are not exceeded. So typical contents will include things like the concrete materials and mix design, the predicted temperature rise of the concrete, which will be based on the concrete materials and mix designs, the element dimensions, the boundary conditions, and so on, all of those factors that I talked about before that contribute to the definition of mass concrete. It will include limits on concrete placement temperatures, which are based on those predictions of predicted temperature rise. It'll include instructions for monitoring the temperatures in the placement to make sure that those limits aren't exceeded. It'll include surface temperature controls, things like applying insulation to make sure that the differentials aren't exceeded, in addition to how long those controls need to remain in place. And then it will also include contingencies. What should you do in the event that you either exceed your maximum temperature or exceed your maximum temperature differential? Or in better practice, what happens if you come close to exceeding those so that you can take steps proactively to avoid exceeding those limits in your actual placement? So there's 4 basic steps to developing a thermal control plan. The first is to review the concrete mixture design and project documents to understand what the system is. Using that information, you conduct a thermal analysis of the mass concrete placements. And then based on those analysis results, provide recommendations for those methods for controlling the concrete temperature and instructions for measuring the concrete temperatures. So we'll address each of these briefly. We'll start with the first 2, which is reviewing the mix design and conducting the thermal analysis. So as we've talked about, mass concrete temperature is a function of several factors, including the element size, the concrete mixture design, construction methods such as the use of formwork or insulating blankets that might help trap heat in the placement, environmental conditions, so the time of the year. If you're placing in warm months, you might have a greater potential for temperature rise, but if you're placing in cooler months, you may have a greater potential for thermal differentials or thermal gradients that might cause cracking. It'll also include things like the temperature of the concrete when it's placed, how long it takes to place the concrete. And then there's also pre and post cooling methods that you can use to help control the temperatures of the concrete, either before it's being placed or after it's being placed. And we'll talk about each of these. But all of these factors influence the potential temperature rise in a mass concrete placement. And to develop a thermal control plan, it's often useful to perform a thermal analysis that takes into account all of these factors in order to predict what are the actual temperatures for the placement. So here's an example of a mass concrete thermal analysis that I'm showing in the figure on the right. And what I'm showing are the predicted core temperature, which is the solid blue line, and surface temperature, which is the dashed green line, and the resulting difference between those, the differential temperature, which is the dashed red line at the bottom. And what this is showing is for a particular combination of element geometry, concrete mixture, insulating conditions, all of those factors that we just talked about, what are we expecting to be the maximum temperature of the concrete at its core? What are we expecting to be its maximum temperature differential? These factors are then considered for a lot of different combinations of environmental conditions, concrete placement temperatures, insulating conditions. So we can use this process, this thermal analysis procedure, to proactively address concerns related to mass concrete placements before concrete's even placed. We use this to develop our understanding of how the concrete element is going to respond to these different changes so that we can specify what temperatures we need, what insulating conditions we need for various environmental exposures and concrete mix designs in order to not exceed the project specified maximum temperature and maximum temperature difference limits. So as we've talked about, the concrete mixture design, the total cementitious materials have a very large impact on the total amount of heat that's generated. There are ways that we can reduce some of the heat that's generated by a concrete mixture. And one of the most effective ways that we can do that is by using a high percentage of fly ash, up to 50% depending on the type of fly ash that you use. Class F fly ash uses or is a particularly efficient material for reducing heat generation in concrete. It can help reduce the amount of heat released by a concrete mixture by up to about 50% of the equivalent amount of cement that it replaces. Class C fly ash is not as efficient as Class F fly ash at reducing temperatures. Typically, it generates about 80% of the heat of the cement that it replaces. And then slag is a little bit less efficient, typically between about 80 and 90% of the heat of the cement that it's replacing. But using SCMs is a very effective way, especially when it's Class F fly ash, a very effective way of reducing your your heat signature for your concrete mix. In terms of temperature differentials and the risk of thermal cracking, the use of different concrete aggregates can also help reduce the risk of thermal cracking. In particular, limestone has a lower coefficient of thermal expansion than granite. And so if you have the option to use a limestone aggregate versus a granite coarse aggregate, because the concrete containing the limestone will have a lower coefficient of thermal expansion than an equivalent mixture that contains granite, the risk of thermal cracking can also be reduced through the selection of those lower coefficient of thermal expansion aggregates. One of the ways that we can also enhance thermal control plan and enhance our understanding of mass concrete behavior is by measuring the adiabatic temperature rise of a concrete mixture. Now, the adiabatic temperature rise is sort of like a heat signature of a concrete mixture. Basically, it's how much heat can be generated or how much temperature rise can be generated by a concrete mixture based on its total amount of cement, its SCMs, and the particular ones that are being used for a project. And we measure this in the lab using a large insulated block called a semi-adiabatic calorimeter. And you can place the concrete into this well-insulated block and measure the temperature rise and use that to understand how that concrete mixture is going to increase in temperature over time. So for this particular concrete mixture that I'm showing in the graph here, this mixture has a total adiabatic temperature rise of about 80 degrees. So basically what that means is if you have a very large element, say a 12-foot thick element, you can expect the interior of that element to rise by about 80 degrees Fahrenheit. So now if you're thinking about trying to limit your total internal temperature to less than 160 degrees Fahrenheit, now you're starting to think that this might be related to your placement temperature. So if you have 160 degree maximum, you're expecting 80 degrees temperature rise. You want to make sure that your placement temperatures are less than 80 degrees to stay under that limit. The second part of developing a thermal control plan, the third step rather, is to provide methods for controlling the concrete temperatures. Now we've talked about controlling peak temperatures by limiting the placement temperature. So that's a method that's called precooling. You can also post-cool your concrete, which is using cooling pipes to draw heat out of the concrete while it's curing. And Jacob will talk in a lot more detail about both of these options. But both of these will come into play in the thermal control plan, how you actually do that. For surface temperature controls, because large temperature differences can cause thermal cracking, one of the things that you often will need to do with a mass concrete placement is apply insulation to the surface of the element to help reduce the temperature difference between the interior of the concrete at its core and at the surface. Basically, the insulation just slows the rate that the surface is cooling, and so that those temperature differences don't become too large. As we've talked about, most specifications limit the temperature difference between the center and the surface to about 35 degrees Fahrenheit, but you can look at alternatives, which would be these temperature difference limits or a performance-based temperature difference limit. And this is a temperature difference limit that is based on the risk of cracking, and it considers the specific coefficient of thermal expansion of the concrete mixture. Recall I mentioned that certain aggregates will expand more or less than other aggregates. It also considers the maturity of the concrete with respect to compressive strength, tensile strength, and modulus of elasticity, and the degree of restraint. And I'll come back to this maturity in just a second. But here's what an example allowable temperature difference limit might look like based on a performance-based temperature limit. It shows for a particular concrete maturity, again, I'll get to this in the next slide, what the maximum allowable temperature is. And what you can see is that for this particular placement, the maximum temperature can be as high as about 50 degrees without increasing the risk of thermal cracking in this placement. Now, going back to the idea of maturity, you might be familiar with the idea of a maturity curve for compressive strength. Basically, what this does is it calculates maturity, which is essentially the product of the temperature it's the temperature history of the concrete. So it's the age of the concrete times its temperature history in a very general sense. Using that maturity, you can plot as a function of maturity what the compressive strength development of the concrete is. And so you can get what's called a maturity curve for compressive strength. And this is commonly used even in pavements and bridge decks and other applications to estimate the in-place temperature of concrete based on its temperature, without actually having to measure the compressive strength of cylinders or cores. A similar relationship can be developed for tensile strength, modulus of elasticity, and so on. And using these relationships, combined with the coefficient of thermal expansion and the restraint that's present within a particular element, you can use that to determine the risk of thermal cracking in a placement and then the allowable temperature difference so that that risk is minimized. The last portion of a thermal control plan, or developing a thermal control plan, is to develop methods for measuring the in-place concrete temperatures. Monitoring concrete temperatures is performed using temperature sensors, and typical placement for these temperature sensors are at the geometric center of an element or at the location where you expect the highest temperatures to be achieved. Usually this is the geometric center, but sometimes, depending on if the element has blockouts or other features, it might be a little bit offset. So you want to install a sensor at that location. And then you also install sensors near the surface at locations where you think the temperature gradients or temperature difference are going to be the largest. So in this particular example, I'm showing a sensor at a corner and at the base of the element, because those would just happen to be the particular locations for this placement where the temperatures were predicted to be the largest, or temperature differences between the surface and the center were predicted to be the largest. We also recommend that temperature sensors are installed in ambient air to measure the ambient temperature and atmospheric conditions as far as validating the thermal model and also understanding what the risk is of thermal cracking if insulation were to be removed. So now I'm going to turn it back over to Jacob to talk about how we actually implement these recommendations in practice.
So this is the fun part. Now that we've specified it, we've analyzed it, developed our thermal control plan, now we get to actually have some fun. And so when we start talking about implementing a mass concrete placement, one of the first things we want to do is a pre-placement meeting. We want to figure out how we're going to monitor and measure the placement temperature, the controls that we're going to put in place for the temperature of the mass element, and how we're going to monitor the temperature of the element as it cures. Pre-placement meeting. So if you're going to install or place a 2 to 5,000 yard mat placement or even a 10,000 yard mat placement, one of the things to think about is having a pre-placement meeting. And there are several things that need to be discussed. Here on the slide, we're looking at probably maybe the 4 top things that we think should be discussed. And so the first one is, who is measuring the placement temperature? Is that the laboratory of record, the contractor, the inspector, an owner's rep, the engineer of record? And so that needs to be discussed at the meeting. And perhaps the laboratory of record does periodic temperature measurements and the contractor measures every truck. Who's responsible for accepting and rejecting the concrete? Is it the place and finish contractor? Is it the general contractor? Is it the owner's rep? These are things that have to be discussed at the pre-placement meeting. So if there's a truck that shows up to the job site that's significantly hot, what do we do with it, and who's responsible for sending it back? Plan B, if you're going to install concrete at a rate of 500 to 1,000 yards an hour, there should be a plan B, whether that's a pump on standby, and there may even need to be a plant on standby. If the concrete plant breaks down, you want to ensure that the concrete placement progresses as expected. Sometimes you may consider a practice placement. So oftentimes on large construction projects, if there's a mass placement, there's often smaller placements prior to that, and you can utilize that as a sort of test run or a practice run to see if you have the appropriate controls in place for the future mass concrete placement. So concrete placement temperature is a very significant factor in mass concrete. The general rule of thumb is that a 1 degree increase in the placement temperature is going to cause approximately a 1 degree increase in the maximum temperature. And again, that's a rule of thumb, but it holds true in most cases. And so as a result, the time of day and the season in which you place concrete, because that affects your placement temperature, that ultimately will affect your maximum core temperature for a given mix design and a given element type. And so as a result, one of the easiest ways to reduce your placement temperature is to place concrete at night or at cooler portions of the time of year. So right now we're having cool portions of the time of year. And so depending upon what your control is over the schedule, you may consider moving up some of your mass placements at this time of year as opposed to doing them in the middle of the summer, where your ambient conditions are going to be warmer. And as a result, your concrete placement temperatures will be higher without the use of pre-cooling measures. And so as a result, as you might expect, the placement temperature requirements for a thermal control plan and given in the plans and specs will impact the contractor and will impact the overall cost to build the project. Infrared thermometers are very helpful for monitoring the placement temperature of concrete. So that's something that can be for larger placements where the service is very high, meaning up to 1,000 yards an hour. It may not be practical or efficient to use a traditional temperature measuring device on the plastic concrete, and it may be easier to use an IR or infrared thermometer as the concrete is coming out of the truck. So here's an example of a concrete temperature specification. This is something I pulled from a project that we previously worked on. And so this is something that most of you folks have seen before. And maybe in some cases you've seen 95 degrees, but typically most concrete specs will have a temperature placement temperature specification. And so the key thing to keep in mind is the temperature specifications aren't necessarily put in place for mass concrete specifically. So again, this temperature specification specifies that the concrete temperature at the point of placement needs to be below 90 degrees. And so this is an example of a project that we worked on where a thermal control plan wasn't actually put into place. And so the contractor and the design team felt as long as the placement temperature was less than 90 degrees, that the concrete core temperature should be fine. And so they installed temperature sensors into the mass element. And what happened is the contractor, per the plans and specifications, was able to maintain a placement temperature of under 90 degrees Fahrenheit. However, for that particular mix, the maximum temperature ended up going up to over 172 degrees Fahrenheit. And so the specs did say that the core temperature needed to be 160. And so then there became a dispute about whose responsibility it was, because the concrete temperature exceeded 160 degrees Fahrenheit. And so pre-cooling of fresh concrete can be done in a variety of different ways. And so we're going to talk about a few of those. One of the simplest ways of pre-cooling fresh concrete is through the addition of ice. And so the general rule of thumb is about 7 to 10 pounds of ice per cubic yard can reduce the placement temperature by approximately 1 degrees. And this will vary depending upon the time of year, and if those bags of ice are actually bags of ice when they're loaded into the truck, or if they've started melting. The thing to keep in mind here is for larger concrete placements, the logistics of adding ice to a truck can be extremely challenging to implement. And so you can see the photograph here on the right, where individual bags are being broken down and then conveyed up into the truck. And so you can imagine if we're adding 100 pounds of ice per cubic yard per truck for example, a 5,000 yard placement, that's a significant amount of ice, not just to obtain, get to the ready mix supplier, but also to load up, get dispersed in the truck, and be able to do that over several hours. One of the more efficient ways, and this is sort of the sledgehammer approach to pre-cooling fresh concrete, is the use of liquid nitrogen. Liquid nitrogen is very efficient at producing lower concrete placement temperatures, and it can do a much better job than chilled water or ice. One of the challenges with this particular approach is not all ready mix suppliers have access to liquid nitrogen. In some markets, there isn't any ready mix suppliers that have access to liquid nitrogen. So for larger projects, you may be able to set up, the contractor may be able to set up its own liquid nitrogen station. But a lot of times, if there's not enough mass elements, the costs for the setup aren't being able to be justified. But the nice thing about it is if it's available in a given market, liquid nitrogen can reduce temperatures by as much as 35 degrees, and in some cases a lot more, depending upon what the initial starting temperature is. Another approach to cooling mass elements is post-cooling. And so the concrete is placed as normal, and then cooling tubes are installed into the element prior to placement, and then water is run through those cooling coils, and it cools the concrete as the concrete sets and gains strengths and hardens and whatnot. So here in this photograph, you can see the installation of cooling pipes, and they're noted here in red, PEX. And so your typical arrangement for cooling pipes is approximately 3 feet on center. So you can either use PEX pipes or PVC. If you use PVC, you would typically use a 1-inch diameter, and you want to space those about 3 feet on center. If you space them anything greater than that, it has a diminishing effect, cooling effect, and oftentimes the startup costs don't justify the minimal effect that it has on cooling the element. And so the nice thing about cooling pipes is they will reduce the maximum core temperature, and then it'll also reduce the temperature control period. So depending upon the type of project that you may have, you may be able to install cooling pipes and reduce the time period in which your temperature control period is in play. And so here we can see a graph here on the right, and what you'll notice is a scenario where no cooling pipes are installed, and you can see that with the solid lines, and so the core temperature is noted in blue. And then you also see a scenario with cooling pipes installed, and that is denoted with the dashed lines. And what you'll notice is there's a significant difference in the overall maximum temperature of the element. So in this particular scenario, we're reducing the maximum core temperature from around 160 to around 140. And you'll also notice that the temperature difference, as indicated in yellow, is significantly reduced, and the temperature control period, meaning the overall time that's required prior to moving forward in the construction sequence, would be reduced with the use of cooling pipes. So after the concrete is placed, you want to monitor the internal temperatures of the concrete element. And so typically the temperatures are recorded every hour. And the purpose of this exercise is to verify that the temperature profile is performing as expected, meaning that the in-place temperature measurements are aligned with the theoretical temperature profile that was calculated during the analysis that was part of the thermal control plan. And ultimately, these temperature measurements will be typically submitted to the design team to confirm that they were within the project specifications. And so on the right-hand side, you can see a photograph of temperature sensors that were installed into a mat foundation. In this particular case, the temperature sensors, the wires were thread through a piece of conduit that was spun up to the top. And so it's just an easy way to keep the wires pseudo-protected during the placement operations. One of the things to kind of keep in mind is to kind of secure those sensors such that they don't press up against the reinforcement. So you're actually measuring the temperature of the concrete and not the temperature of the reinforcement. And so after the concrete is placed and the temperatures are being measured, you'll want to apply blankets to the concrete surface. And so for a lot of folks, this is somewhat counterintuitive because the thought process is, don't we want to get the concrete to cool down? Why are we putting blankets on it to keep it warm? And so one of the things that we also remember is that we're concerned about the temperature difference between the core of the concrete element and the surface, and we're trying to minimize those differences to mitigate thermal cracking. And so blankets are put on the surface of the concrete to help mitigate thermal cracking due to large temperature differences. And so here on the right-hand side, you can see multiple layers of insulated blankets that have been applied to a large foundation element. And so in some instances, a lot of blankets are only 2 to 3 in terms of its R value. So you may have to add multiple layers to get an equivalent layer value. One thing to keep in mind if you have larger elements and you're a contractor is that some of these insulations can be a long lead item and may take 1 to 3 weeks to actually get onto your job site. So if you are using absorptive blankets, something that's going to absorb moisture or water if it rains, for example, you'd want to put down some plastic sheeting. And so you can see in the right-hand side of the slide that plastic sheeting was installed because an absorptive blanket was used. And so the idea here is that the water will have a cooling effect and can cause your temperature differentials to increase. And so that's why we recommend that wetting of that mass element should be avoided. So many specifications often require that a wet cure be applied to concrete elements. It's our position that wetting of the mass concrete element has a cooling effect and increases the likelihood of larger temperature differentials. and can therefore increase the likelihood of thermal cracks. If you have if you have reinforcement that's protruding from the surface of a mass element, that reinforcement should also be insulated as well. And so you can see an example here on the right where they did a pretty decent job of covering the surface of the concrete, but did not insulate the reinforcement. So here's an example of some insulation that was installed on some formwork. And so not only does the insulation need to be installed on the surface of the element and on the formwork, but it needs to be effectively installed. And so in this particular instant, the contractor decided to put the insulation in between the ribs, so that way when they erect the formwork and reuse the formwork on another mass element, they didn't have to go through the task of removing the insulation and then putting it back on. This would speed up their is. The unfortunate thing in this particular instance is the type of insulation that they used was reduced or is less effective because, for example, if you put in an R5, due to the placement of the ribs, it effectively was acting as an R2 or an R2.5. And so if you do something like that, you have to keep that in mind. So here's a graph that shows an example of an insulation being ineffective. And so in this particular case, they utilized an R5 insulation. And what you'll notice is that the surface temperature sort of mimics and kind of follows the ambient condition shown in black. And so the surface temperature is shown in the dashed line, and it kind of follows the ambient conditions. And so while in this particular case, the insulation was an R5, it was several years old and had worn down, had rips and tears in it, and as a result was no longer acting as an R5. It was acting like something less than that. And so you can see here in this area at the beginning of the temperature control period, the surface temperature sort of is aligned with the ambient temperature. So how long does the temperature control period last? Well, it depends. As Elizabeth said, that's a favorite answer of ours. Sometimes the specifications state the temperature control period, but in general, the temperature control should be maintained until the risk of cracking is minimal. So in summary, for mass concrete, the primary concern is temperature of the concrete element. And so the two things that we're primarily concerned with is the temperature differentials between the core and the surface layer contributing to thermal cracking. The second thing that we're concerned about is high internal concrete temperatures can later lead to delayed ettringite formation, which would cause some expansion and cracking of the concrete element. And so as a result, we want to be able to formulate and develop specifications that define the mass concrete. We want to be able to analyze it, prepare a thermal control plan, and then use those things to help with the concrete placement efforts. And so if you're a specifier, some of the key things that you need to be thinking about when you're specifying mass concrete is identifying the mass elements. And this can be done by size, geometry, cementitious content, surface area. There's different ways that you can do it, but it needs to be clearly identified in the project plans and specifications such that the contractor can plan it and bid it and execute accordingly. One thing to realize is that we're no longer using concrete mixtures with relatively low cementitious contents. So as structures are getting larger, spans are getting larger, column spacing is getting larger, we're using higher strength concrete that has more cementitious materials in it. And as a result, these high-strength structural concrete mixtures can generate significant amounts of heat, things that we haven't necessarily dealt with 20 or 30 years ago. If you're specifying mass concrete, you should maybe consider allowing the contractor to submit a performance-based temperature limit. And that can, in some cases, cause the contractor to act in a more efficient way and move the project along in a more timely fashion. If you're a specifier and you think you have mass elements on your project, one of the easiest things to do is require that the contractor submit a thermal control plan as part of the submittal process. And in some cases, it might even make sense for that to specify that thermal control plan be prepared by a licensed professional. And as the engineer of record, that helps manage some of your risk and keeps things moving in a diligent fashion. And the final thing to kind of think about is think about omitting the wet cure of mass elements. That can cause a wet cure of mass elements can increase the risk for thermal cracking. So when you analyze mass concrete, some of the things to think about is beginning with the end in mind, Stephen Covey would say. And so you can use low heat concrete mixtures with the use of supplemental cementitious materials. So things like fly ash or gray, class F ash, even though it's difficult to get at this time period, is great for mass concrete elements. And you can use them in very high dosage. We've worked on projects where mass elements were using 40% class F ash and 50% class C ash. Other things to consider are post-cooling options. Some of those things, if the project is right, that can expedite the construction schedule. If you're doing concrete elements that are near a large water source, for example, like a river, you can use that cool water, feed it through the cooling pipes without too much effort. The other thing to kind of comment on is utilize the RFI process. I love the RFI process. Many folks think that it slows things down, but I think the RFI process is great. We have good projects, plans and specs, but the RFI process allows for folks to explore creative options for tackling challenging projects. And so if you want to try and figure out ways to solve different types of problems, you can utilize the RFI process to help that along. And finally, key things to think about when placing a mass element is conduct a pre-placement meeting, as we discussed before. Understanding the pros and cons of ice, liquid nitrogen, and cooling pipes. And there are advantages to all of them, and there's time and costs for each one of those things as well. And then monitoring the placement of the incoming trucks. And then again, the final thing is planning for the temperature control period within the construction schedule. Sometimes the elements need to be insulated and covered up, for 1 week, 1.5 weeks. And so that needs to be factored in to the temperature control period, particularly if you're a contractor that plans to reuse that formwork for future placements. And so that is the end of our presentation. We thank you, and I think we're going to take some questions.
Okay, let's take our first question. What is the typical workflow for developing thermal control plans between engineers, ready mix suppliers, and contractors? If performance-based thermal control plans are based on specific mix designs, are there design iterations of thermal control plans?
Jacob, did you want to take that, or would you like me to? I'll go ahead since it seems like Jacob might be muted. So the typical workflow is ideally, if we can get involved in developing a thermal control plan early in the process, it helps everyone. It helps in terms of selecting a concrete mix design. because a thermal control plan or a thermal analysis can evaluate a variety of candidate concrete mixtures to determine what might be useful for a particular project and what might be the easiest to help control concrete temperatures and temperature differences. So typically the earlier a thermal control plan can be developed, the better. It's often performed at the direction of the contractor, with the engineer of record then reviewing and approving the thermal control plan for use on the project. And ideally, the thermal control plan is prepared well in advance of concrete placement so that those pre-placement meetings that Jacob discussed can be held. Jacob, I don't know if there's anything else you wanted to add.
So as you indicated, I put myself on mute. So no, that was a fantastic answer, Elizabeth.
Thank you.
All right, let's go to our next question. Does fly ash or slag count toward total cementitious material?
All right, so this is actually a question that I meant to clarify before and did not, so I'm glad it was asked. So in this graph from ACI 207.1, it talks about equivalent cement content. So I've been using the term cementitious content, but really I should be talking about the equivalent cement content. Cementitious content is going to include the cement and SCMs like fly ash and slag, but the equivalent cement content is actually going to essentially be related to the contributions of those different components to the heat generation. So like I mentioned before, Class F fly ash only contributes about 50% of the heat as cement. And so its factor in this calculation of equivalent cement content is only about 0.5. And ACI gives guidance on how to calculate that for different SCMs. So yes, the total cementitious content does include fly ash, slag, and so on. But what I probably should have stated was really that it's the equivalent cement content that's governing a lot of the temperature rise in mass concrete. And that really depends on how much heat is released by those SCMs.
Okay, our next question. What is the reason you'd have cracks on concrete when monitored with sensors, when monitored mass concrete did not exceed differentials?
This is a great question. I love this question. And oftentimes it is thermal cracks. It could be plastic shrinkage cracking as well, but it could also be thermal cracks. The interesting thing is that you can actually get thermal cracks, and it depends on the mixture, and it depends on the heat profile of a given mixture. But you can get thermal cracks when the temperature differentials are as little as 15 degrees Fahrenheit. And so we've seen some instances in mass elements where the contractor actually complied with the 35 temperature difference specification, and they did still end up with some thermal cracks. And so again, the thermal cracking is a function of time and temperature. And so if the concrete doesn't have enough strength at a given moment in time to resist those early age tensile stresses, it can crack.
Okay, our next question. If the internal concrete temperature exceeds the thermal control plan by 5 degrees Fahrenheit or 10 degrees Fahrenheit, is this a problem, and what are the next steps?
So the risk of exceeding the maximum temperature is the risk of DEF happening. DEF requires a few different factors, which Jacob had talked about earlier. Let me pull up that slide really briefly. So it requires, first of all, temperatures exceeding 160 or whatever the maximum is for the project. But it also requires exposure to significant moisture in service and a materials chemistry that's susceptible to DEF. So if temperatures exceed the specified limits, usually the next steps are to evaluate the risk of DEF. And that can be done by evaluating the materials chemistry or through doing petrographic analysis, where you actually look at samples of the concrete under a microscope, which is actually what this photo is from, and determine if DEF has happened or if there's indicators that there's a risk of DEF happening in the future. So it's not necessarily a deal breaker, but it does require further analysis.
Okay, our next question. When third-party testing is done on the concrete, are temperatures taken at that point?
So it depends. So most specifications require the concrete to be sampled at the point of placement. And then as a result, the temperatures will then be taken at the point of placement. Sometimes the concrete is sampled at the truck. The key thing to kind of keep in mind for mass concrete is when we talk about placement temperature, we're talking about the temperature at the point of placement, not necessarily the temperature of the concrete that's coming out of the truck. So depending upon how you're placing the concrete, you can see an increase in temperature from anywhere from 2 to 4 degrees from coming out of the truck at the point of placement. And so sometimes the pumping operations and other methods of conveyance will cause that temperature to increase. So it's very important that for the purposes of the thermal control plan, that some of the temperatures, if not all the temperatures, are being measured at the point of placement, not necessarily just what's coming out of the truck.
Okay, our next question. What is the average length of time for monitoring / the temperature control period, and how is this determined?
So the temperature control period is basically defined by how long you need to keep your insulation in place until the risk of thermal cracking is minimized. And so we talked about thermal cracking being driven by the difference in temperature between the interior of the concrete and the surface. And so really it's how long until the temperature at the interior of your placement is within the allowable temperature difference from the ambient temperature. So for very large placements, this could be several weeks, on the order of 3 to 4 weeks or so. But for smaller placements, it might be as little as, 3 to 5 days. It really depends on the specifics of the placement and the results of the thermal analysis.
Okay, we've got time for one more question. This looks like a good one to end things on. I'm assuming WJE can develop the mass concrete temperature control plan. Not a question, but you can go ahead and answer it as one.
Absolutely.
All right, keep it short and sweet. Okay, so that is all the time that we have for questions today. Thank you, Jacob and Elizabeth, for the great presentation. We hope it's been educational, and we thank you for joining us. If you have any questions about the content in today's presentation, please feel free to reach out to Elizabeth or to Jacob. And if you have any questions about today's webinar or any other WJE webinars, please reach out to me, Liz Pimper, at lpimper@wje.com. So again, thank you so much for your time, and we hope you have a great rest of the day.